All right, so you guys are writing the very first page of section 9.2. We're coming back to this in just 1 second. But looking at this sequence, you're kind of like, most of you probably don't quite get what the pattern is because it's not shown super clearly. It is shown. It's shown in A2 minus A1, A3 minus A2, A4 minus A3, all being the exact same D. But most of you would rather me show it like this. You're going to add D to get from 1 to 1. Sense? Your jumpity jump jumps will just be plus D, plus D, plus D, plus D. So your recursive formulas could be, P.S., common difference, snazzy name for D. Can always be found by subtracting 2 terms of any arithmetic sequence or arithmetic sequence. But to see the common difference, if we were to define this recursively, we could just take the previous term and always say, just add D. But the nth term formula will be a bit more complicated. So finish filling in those couple things because I think it makes it a lot more clear if you just say, hey, the jump is plus D, the next jump is plus D, the next jump plus D. So that common difference, D, would just be thrown into a recursive formula. I don't like that being read. Could just be thrown into a recursive formula saying, hey, the pattern is just add D. Okay, we're coming back to section 9.2 in just a second. Let's go back and finish 9.1. You guys were playing around with this. Where do I find a sigma, a summation, because it's a sum, in my calculator?
Math.
Yep.
0.
Math 0. Thank you, thank you. If you have an old calculator with a yellow button, it can't do this at all. Go team. Lo siento. The best way you could do it is you could make in your stat plot, you could go ahead and try to make a list of the sequence and then try to add things up. I guess you could do it that way. It'd probably be easier just to plug in and add it in one big old string in your calculator. But anyway, for this sigma, some of you guys got stuck when you were trying to plug this in because you were like, wait a minute, hold on, who is or where is infinity? Why isn't this working? First of all, what did you guys use for this little I? Capital I? Okay. So alpha, where is capital I? Sorry, the little x squared? Okay. So I is equal to, put it over here. Hopefully, you weren't sure about that, but you could have done your little fraction you do, right? In your little fraction you do, you could have done 3 over 10 to the, good, 10 to the, you have to use the same variable you used over here, which you could have done I, you could have done K, you could have done N, you could have done X. But since we put I, let's go ahead and use I again. So alpha I. If you try to run it right now, it says no. Why? Because go to, you didn't put in a top bound. Now, if I just told you there is absolutely no button in the calculator that fully encapsulates or shows, signifies, notes infinity. Wait, pause. What was the hint I gave when you guys were looking for the infinity symbol? It actually says third partial sum. Partial, what does that mean? Not all the way. Sure, that sounds good. So all the way would be infinite, meaning adding them all together. Meaning if we were to actually start plugging in, because remember, a summation, what the sigma denotes, says plug in 1, plug in 2, plug in 3, plug in 4, until, okay, well, plug in 1, is that okay? Plug in 2, plug in 3, infinity says keep going. Third partial sum, part, not the whole thing. What do you think partial, third partial means if you have third coming before partial? What do you think it's talking about? Kind of, till the third term, yeah, that makes sense. Till the third term, only till the third term. So take part of it, what part? Well, only till the third. Does that kind of make sense? The first partial sum would just be the first term. Second partial sum would be the first 2. Third partial sum, the first 3. So the 10th partial sum would be the first 10, exactly. So third partial sum, we could write it in snazzy notation using that little S sub n notation, sum of the first 3. So letter A is saying, don't do the whole thing, don't solve the whole thing, just the sum of the first 3. So did anybody figure that out and plug in what's 3/10 plus 3/100 plus 3 thousandths, or in your calculator, did you just say, I'm going to stop at 3? What do you get?
I get 3 over.
Partial sum, it's the sum of 3. So I want when I is 1, I is 2, I is 3, or you could literally just plug in and add them all. Because 10, 10 squared, 10 cubed. I just went ahead and solved that. Now, some of you guys would have gotten 333 over 1,000, but I'm not sure that's quite as easy as thinking about it as a decimal, which would be?
0.333.
Hey, you didn't even need your calculator to tell you, hopefully. Because what's going to happen as you keep on adding 3's over higher powers of 10? 0.33333333333. What is the infinite sum from I equals 1? Well, the infinite sum is from I equals 1 to infinity of 3 over 10 to the I, 1/3. 0.3333333333333. Wait, what if I had asked you guys at the very beginning, what would happen if you keep on adding and adding and adding and adding and adding to infinity? You probably would have thought it's going to keep on getting bigger and bigger and bigger and bigger, but it doesn't keep expanding. It keeps getting closer to one value. So the infinite sum is a finite constant. The infinite sum is a finite constant. This idea is kind of shown around my room, and we'll talk more about it when we get to chapter 12. But this is a good one to use. This is a good one to use. This is an artist. I think all of these. Are all of these? Yeah. All of these are by M.C. Escher, not the verses. That's by Jesus. Well, by God. But Jesus is the Word, right? In the beginning was the Word, and the Word was with God, and the Word was with... Anyway. So, coming back. The pictures by M.C. Escher. He loved to play with perspective. If you guys ever... You probably have seen this one. There's one where he's holding like a chrome or a metal ball, and he drew himself. That one's a really cool one. He drew his own reflection. There's another one where there are two hands drawing each other, and so you're trying to figure out which one is his hand and which one is the hand that he's drawing. And then he also likes one where there's an upstairs, downstairs, and you can't exactly tell what's the right one. It makes it look like people are walking down and up at the same time. Or there's another one where you see water that's seemingly flowing down and flowing up at the same time. He likes to play with perspective a lot. He liked to. He's no longer alive. But this one, he studied a lot of geometry in a lot of his drawings. These are actually fishes. You might not be able to see it super well, actually. Hold on. I think it's just command stripped. There we go. What? Mod Podge. Very fun. Get a canvas from Michael's and then paint it and then print off a picture. And go team. This picture, they're little into the fishes as this picture gets closer and closer to the outer boundary. Onto the number of fishes. The number of fishes are increasing, right? If they're increasing by fractional amounts, what's technically going on at this edge? The number of fishes are approaching infinity, but as they get smaller and smaller and smaller, cut into fractions, is this circle going to ever expand? No. So the infinite is finite. Interesting. And here's another example of it. The infinite is contained by, or converging, convergent, divergent, converging to the finite. Interesting. Now, does that always happen? Can I give you an example? Change your sum. Instead of 3/10, change it to 10/3. So go up, steal, I should put my marker down. I want you to go steal the exact same expression that you just took, but instead of 3/10, can you make it 10 over 3 to the I? Just changing one little bit. It's impossible. When you go to the third, right? Here's a question. This one that we just did a second ago, the 3 over 10 to the I, we never really had to struggle with the infinity thing because the infinity thing we actually saw was 0.333333, and so we kind of just jumped ahead to 1/3. using our previous knowledge in math. This one, if we wanted to go to infinity, you could change this to a fraction, math frac, right? No, not fraction, sorry, decimal. Math decimal, there we go. Does this look like something that we recognize very easily? I don't know about you, but I don't. So, question, if we can't plug in an infinity button, wait, what is infinity? What's its value?
Infinite.
Careful. There is no value. I agree with that. So, infinity is not a number, it's more of an idea, right? Infinity isn't a number, it's more of an idea. Hold on, pause. So if I can't plug it in as a number, let's think of it as an idea. If I'm going to infinity, that means I'm taking steps towards infinity. So question, how could I make this summation go closer to infinity from where I'm at right now? I heard something about start, I heard something about variable. Well, that's why I couldn't really do anything, because that doesn't really help me with anything. My question is, how do I go from the third partial sum and get closer to infinity? If I can't plug in infinity, let's head that direction. So how could I head that direction? Nick?
Wait, is 3 still getting the exponent?
Yes.
Even when you flip it? Or is 10 getting the exponent?
Oh, 10 was getting the exponent before, wasn't it?
Yeah.
So now 3. I just switched the numbers only. The numbers only. But thanks for checking. If I was switching the whole thing, you're right. The 10 would need to be the I. How do I get closer to infinity? Just keep adding, sure. So instead of stopping at 3, then stop at 10, sure. I mean, we could do 4, but that's going to be baby steps to infinity, which will take a long time, yeah? If you've ever seen What About Bob, baby steps to the elevator. Anyway, how do I get even closer? It's an old movie, Bill Murray. Anyway, it really makes me frustrated every time I watch it, so I just don't watch it anymore. The poor psychiatrist. It's just a struggle. How do I get closer to infinity? 100.
Put in 1,000 and it said error.
It said error?
Yeah.
Why? I'm going to go to 1,000 and see if mine says error. Does anybody else put in 1,000?
It overflows.
Yeah. Okay, now, hold on. That doesn't mean that you couldn't go to 1,000 with a better operating system. The problem is our calculator does have limits. So we just found limits in that it didn't internally combust, but it did kind of get mad and said, you're asking too much of me. So hold on. Let's go back. Our jump from wherever it was, from 10 to 100 was a little too much, like a little too fast. We couldn't quite tell exactly what's going on. Let's go ahead and jump instead to 50. Whoa, if I can get there, hold on. Ugh, this calculator. Can anybody jump to 50 for me? I'm just going to get out of my calculator. It's taking too long. You got 5? Okay, jump to 25. Wait, but when you went to 100, it was 5 also. Thank you. Thank you. Thank you. Okay, hold on. When you go to 25, what's going on? It's 5? This is so boring. When you go to 15, what's going on? Wait, do you guys see any sort of progression? So when we plugged in 3, it was 4.8 something. When we plugged in 10, it was 4.999 something. When we plugged in 15, it was 4.999 something. And then when we plugged in 100, it was 5. When we plugged in 50, it was 5. What's going on? It's converging again. 4.999, 4.99999, 4. Now, how many decimals can your calculator hold? At some point, it always has to round because it can only hold so many digits on the screen. So what's going on at 50 and at 100 and at 25? There's so many points. No. It just says 5. Is it really 5? No. But is it getting closer and closer and closer and closer and closer and closer and closer to 5? The answer is yes. Now, let's change one more thing. Let's change what Nick said. Instead of the I being in the denominator, can you guys put it in the numerator instead? Can I just clear this? There we go. So take the I out of the denominator.
I got 3.703703704704 e to the 19.
Ooh, e to the 19.
It gets exponentially larger.
It gets larger. I'm not sure it's exponentially larger, but it does get larger.
Doctor, you didn't understand this concept. You have to explain this. I'm not kidding. Ask Ryan. We have to explain this to her. We're like, if the numerator gets bigger, the denominator's going to
Overflow. That's not going to work. Michael, what did you plug in to get the big number that you quoted?
Oh, I had 20 in the top. Never mind.
No, that's not a bad thing. Mine was overflow. It was too much for my poor little calculator to handle. But if I go ahead and delete this, you had 20?
Yeah.
Let me just go 30. Let's see if the calculator can handle that. So 20 was e to the 19. Now it's e to the 29. Do you guys see what's happening?
I see.
It's getting bigger and bigger and bigger and bigger and bigger and bigger and bigger. Why? Because you're adding larger and larger and larger and larger and larger values. So question, just because you're going to infinity, will you always get an infinite answer? No. But can you get an infinite answer? Yes, it can never expand. That's totally true. Vicky, put your notes down and look up here. Vicky, hi. Okay, so you can sometimes be ever expanding, but you can also just be getting closer and closer and closer. You're still expanding, but in a way that you're converging. So the number of fishes expands to infinity, but the space it's held within is finite, kind of like 1/3. All of that to say, infinite. Is there an infinity button in your calculator? No. So how do we do it? You don't plug in infinity, you plug in bigger and bigger numbers. Can your calculator always handle really big numbers? Sadly, no. But can you still take steps towards infinity, kind of gauging what your calculator can do? And can it kind of show you whether those sums are getting closer and closer to something or whether they seem to be getting farther and farther away from anything finite. Does that kind of make sense? Interesting. Okay, section 9.1, let's grade real fast. It's going to be on the video if it's too fast for you. Overflow, right, after that? That's good to know. So some of you are like, well, why can't your calculator handle it? There's lots of digits. Nick just said it can go to times 10 to the 99th, and then it freaks out. However, if you were to go to some really cool computing site online like Wolfram Alpha, I bet it could go, well, I'm not sure it's software per se. You're not downloading it onto your hard drive. I mean, it is a program, that's true. But Wolfram Alpha could probably get you a few more digits. Number 4, factorial. Oh, I almost got it. There. Okay. It's good sometimes. It's a little annoying other times. Okay. Number 4, factorial. Number 4, factorial. You might not have meant how it came across. It was just really funny. Sorry. Number 4, factorial. Number 12. You guys were just trying to find the first 5 terms? Okay. So 3, 12, 11s, 9, 13s, 24, 47s, 15, 37s. Could, I suppose. Sometimes decimals are nice, like today, the 0.3, the 0.33, the 0.333, as opposed to 333 over 1,000. A lot of you wouldn't have realized what was going on. But usually fractions are better. Number 22, same thing, wasn't it? Just plugging in. But did you guys notice this little negative 1 to the ended up alternating the signs? I use alternating for a very specific reason. My car people, alternators. Yeah, but I was trying to say alternating like alternate, never mind. But alternators, think of that. It's very similar, alternating, going back and forth. Anyway, don't alternators kind of like even out the battery, sending the current or something like that? Isn't that what it does? Yeah. Number 60. I've had mine go out, so I kind of figure it. Because if it's overloading the battery, then the battery dies, and then it's just... Anyway, first 5 terms. But this one was a little weird. You were supposed to stop at a sub 4 because n started at 0. It was one of those ones. But you still were just supposed to find the first 5. This one you're playing with factorials a little bit. No, it's called an alternator. Alternator. Isn't it an alternator?
It's alternates.
Yeah.
The card, right?
Yeah. Okay. I thought someone said it was alternate. I was like, what? It's I had to like say it a few times. It's alternator. Guys.
Hey, don't threaten. Don't threaten.
Hey, did you guys get 64? It was like the ones we did in class. Did you do it without your calculator? Because calculator, you might have done the division and messed it all up. All right. Final answer, 495. And then you guys were using either the plug and chug, plugging in 0 all the way to 4, starting with 0 is a little different, or using your calculator. Any questions on homework? Because you guys are just goofing off now. Questions going once, evens or odds? Jackie. 65. Other questions? AJ. 57. 57, 65. Anything else? Ooh, we have a few. All right, let's start with 57. Jaden, anything before 57? 49. All right. So in number 49, we're in chapter 9 now, yeah? Go team. I probably won't solve it all the way out, but let's go ahead and see where the confusion was. So number 49, I think it's this page. Ah, it's not. There it is. Right, the first 5 terms. Wait, guys, this is great because this is like section 9.2. Why am I saying that this sequence is arithmetic? Like the ones that we wrote about in our notes. P.S. You can have your notes ready, my ones that are just bored. Why am I saying this is recursive, a recursively defined arithmetic sequence where you just add a number every time? What are you adding every time in this sequence? No, you're not adding A of K. Remember, to get to this one, you start with the previous one. What are you doing every time? What's your pattern? And it's subtracting by 4. How can we write that as addition? What would my D be? Subtracting 4 is the same thing as adding. Got it. D would be -4. So how do you write the first 5 terms? Start here. What are you going to do to get to the next term? Yeah, add -4 or subtract 4. So the next term, 24, 20, 16, 12. How many terms? I lost count. But just keep minusing 4 every time. Then Jackie, you said 57, right? Oh, someone said 57. AJ. 57. Write the first 12 terms of the Fibonacci sequence. And the first, well, we already did that one yesterday, the day before. Remember Fibonacci? What's that sequence again? Kiri. Hi, wake up. That's the sequence, but what are the terms? They just want the terms. So it'd be 1, 1, then 2, then 3, then 5. Okay, we got the pattern. Continue it to get 12 terms. Then they said to write this one down. Now this one's a little weird because there are n's, but do you guys see how if one term is defined in terms of the others, it's recursive again? Okay, so because if you were to plug in n as 1, you can't just like solve it, you have to get the terms. So they tell us the first 10 terms of the sequence given by. So the notation was weird. They said a sub n was Fibonacci. So you had to use Fibonacci to get the next one. So when this says a sub n plus 1 over a sub n, what they're saying is look up here at Fibonacci and take the second term over the first term. So second term over the first term would be 1 over 1, 1. Then take 2 over 1, 2. Then take 3 over 2, 3 halves. Then take 5 over 3, 5 thirds. Does that make sense, AJ? So it's saying go to Fibonacci and then divide the latter by the prior or the earlier. So divide, 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 divide. Okay, Jackie, I think yours was next. Number 65. Ooh, he was a factorial one. Guys, help me out because this was confusing yesterday. This was confusing as soon as the numbers were gone and the variables were there. Help out. Both of these factorials, all factorials, count up starting from 1, right? So 1, 2, 3, etc. This one's going to end at, well, this one's a little easier. This one's going to end at n. Does this one hit n? It hits n, and then it goes ahead and goes 1 more. So think, if this was a 10, this would be 11. So it would hit 10, it would just go 1 more to 11. If this was 100, this would hit 100, but 101, it would go 1 more. And why am I making that point? What can I say for all of these? The only one left is n plus 1. Ooh. Now you can't really get that by subtracting or doing anything here. You have to think of, wait, it's everything up to n plus 1, including the number before, which was n. Everything up to n, oh, those all reduce. Just that one is left. It's interesting. Factorials are interesting. Okay, I covered AJ's, I covered Jaden's, I covered Jackie's. I think we might have had one more. 85. That's right, AJ, you had a second one. 85 is chilling right over here. Sheep, sheep. Is this where you're trying to? Okay. Kiddos. For those of you that are bored, notes should be open. Notes should be open. I may do yours at home. Notes should be open. For the rest of you guys, you're looking in your homework spirals, trying to see if you know why you did what you did, not that just you copied Calc Chat. Number 85. You're trying to rewrite. Now, guys, could we type this whole thing in our calculator if we need to find it? Is there any notation that takes a sum that follows a pattern and condenses it into one nice little math function? Summation. So these directions said, rewrite this as a summation, then we could plug and chug it into our calculator once, which would be a lot nicer. Now, do you want to use the I, because that's what we did in class? We can use I. Okay. We could use X also, totally fine. I'm going to have I start at the first number I see kind of being plugged in. See how these are counting up? I'm going to have I start at 1 and go to 20. Does that make sense? Okay. Now, what's my pattern? I need to put a pattern here to tell it how to plug in or what to plug into. What's my pattern? Yeah, Lainey. Check it. Does it make sense? 1 over 1 squared, 1 over 2 squared, 1 over 3 squared, 1 over 4 squared. I had to use a variable so that I could be changing. This almost works. What else do you notice in this sum? It's wait. We had one that alternated, didn't we?
Yes.
Where was it? Yeah, the alternator. It's alternating. What was different in the summation, well, in the pattern that made it alternate? That? No. That? No. That? No. I need to do -1 to a power that the power changes every time. Because if -1 is to an even power, it's positive. And if -1 is to an odd power, it's negative. So I go ahead and throw in my summation. Oops. Where was I writing? I was writing somewhere. Oh, in the PDF. I need to throw a -1 into the summation using my variable to say, why wouldn't I just do I? Because if I did -1 to the 1, what would my term start out being? Negative. Oh, nope. I need it to be positive, so let's do I plus 1. Check it. So what if I do -1 to the 2? Isn't that positive? What if I do -1 to the plug-in 2 now, 3? Oh, that's negative. To the 4, oh, that's positive. To the 5, oh, that's negative, etc. Does that kind of make sense? Yes. This little -1 is my alternator. Go team. Back to notes, section 9.2. Arithmetic. Nice thing is we've already kind of looked at a lot of arithmetic stuff today. So picking up where notes left off. They said whose nth term is 4n plus 3. I could rewrite that using notation from yesterday. A sub n equals 4n plus 3. How am I going to know whether or not this is arithmetic? Yeah, I guess I could stare at it a long time, but wouldn't it be easier to say, hey, who is A1, who is A2, who is A3, and ask yourselves, is there a pattern, right? So if I plug in 1, just quick mental math, if that's okay. 4 times 1 is 4 plus 3 is 7. 4 times 2 is 8, plus 3 is 11. You know what? If it's plus 4 every time, we're good. Plugging in 3, it's going to be 15. Do you see it? Is it arithmetic? Yes. And how can you say that it is? Because there is a common difference, and it's 4. That's my rationale. That's my proof. Every time you're adding 4, yeah, it's arithmetic. Looking at letter B, I mean, this one's kind of nice because we're just looking at it, right? The pattern is 1 squared, 2 squared, 3 squared, 4 squared. But hold on, even though there's a pattern, wait, to be arithmetic, it has to be very specifically adding the same thing every time. And if you guys look at it pretty quickly, can't you say, wait, no? It's not adding the same thing every time. Ryan, make sure that phone is, if that is a phone, off and under your desk. So the answer would be no, and why? There is no common difference. No, and there is no common difference would be the rationale as to why. There's a pattern, yeah, but it's not arithmetic. There's a pattern, but it's not arithmetic. I see a couple of you still writing, so let's dual page as we go on. If they gave us a sequence, I guess technically, in order for it to belong in this section, it has to follow the pattern. So you guys look at this one. Wait, it's not adding every time. Wait, it is. It's just adding by a negative. Because if I subtract 5, and if I subtract 5, and if I subtract 5, oh yeah, that does work. So my common difference would be negative 5. Right? Now, I'll get you guys writing that formula in just a second. There are 2 main formulas we have to use this section for arithmetic. Now that we're zooming in on a specific type, we can just talk about him and his nth term formulas and his nth partial sum formulas. But let me just try to introduce this for you. If I needed to get to not the first, second, third, fourth term, but if I needed to get to the 20th term, I want you to think of something. How many jumps of plus negative 5 did I need to take from the first to get to the fourth? Just 3 jumps. So how many jumps would it take to get to the fifth? So how many jumps will it take to get to the 20th? So I can say the 20th term is going to equal the first term plus 19 jumps of negative 5. And the pattern will be that every time to get to the nth term, you're always going to start at the first term and take n minus 1 jumps of d. The operation is multiplication, because when you add and add and add and add and add, you can just say that you're multiplying, bless you, by factors of common difference. Nick.
So, but couldn't you write like a of 20? I mean a of 19 minus 5.
Totally. But the problem is, remember, unless you're using your calculator, you'd have to get to that 19th to do the minus 5. And to get to the 19th, you have to get to the 18th. You'd have to do all the jumps in between by hand.
Couldn't you write the 19th term, whatever that is? Like, you have to give a value for the 19th?
Well, if you're just writing a formula, no. But if, like in this one, you were trying to find it, it'd be a lot easier to do this math than to actually have to get all 20 or all 19. Does that make sense? Yeah. If you're a programmer, yeah, totally do the recursive, make the calculator do it. But this one would be 2 ultimately minus 95 if we were to solve, instead of having to jumpity jump to get there. 5 and 4, 95, yeah. So when we come over to this example, and when it says, find a formula for the nth term, okay, a sub n. Since it's arithmetic, since it's special, Nick won't be doing many recursive because it has a pattern where we do have nice formulas to go straight to. What do we know? D is 3 and 1. Oh, well, we have a formula. We can say, they didn't tell us which term, but that's all right. We'll just get the formula down by saying start at 2 and always take n minus 1 jumps of 3. And you could box that and be done. But, I mean, we know algebra, so you could also do some things like distribute the 3 and simplify. So it could also look like negative 1 plus 3n or 3n minus. So sometimes these nth term formulas might look different, but they all come from the same original formula. And you have arithmetic. If you're a highlighting person, you might want to highlight that box. It's pretty important. So what if they were to give you something like this, where they don't tell you anything but there's the sequence, figure out when this 129 will occur. Here's a sequence, figure out when the 129 will occur. I mean, you could just add, wait. You can't do anything until you figure out the pattern. What's the pattern? Yeah, adding 7 every time, so this will be arithmetic. So could you go in your calculator and could you add 7, add 7, add 7, and see that it lands on 129? How many jumps? I suppose. But what else could you do? You could say, you know what? There's a time when the nth term will be 129. I'm not sure when, but let me go back and use the formula. Use a sub 1, which is 3. Add to it n minus 1. I don't figure out. But I do know d. Can I solve? And with some pretty quick algebra of distributing the 7 and combining 3 minus 7 is negative 4 and adding it to be 133, we could end up with n is equal to 19 pretty quickly. But it's using that formula that we saw. Now guys, I could do some other examples where we play around with a sub n, but since time is getting short and there's really just one more important idea, let's skip that example for now. Maybe we'll come back to it in Workspace or something, but let's just finish off with this. And I might tell you on Monday the story behind where this formula kind of first originated. But the nice thing is it's really just a formula that you guys are going to need to use for the nth partial sum. And for the nth partial sum, we can say, to find s sub n, divide n by 2, add the first term plus the nth term, and don't forget, you can always go pause, find the nth term if you need it using the other formula. So sometimes you're going to have to use one, then the other. Now, kiddos, we've covered the most important formulas of 9.2. Do the best you can in homework. Get as far as you can. I would say fully attempt it. But realize there might be a few tricky examples that we might need to do hashing out on Monday. On Monday, we'll finish up a few examples on 9.2 with your questions from homework. And then we'll start 9.3. Bye, guys. Happy weekend. Happy Friday. If you need anything, let me know. Yeah, please. Got it? What were you guys playing with back there? Joe and Josh. What were you? Oh. You need one of those like fidget box things.